I guess I'll start with some propaganda like Aaron and Jacob did. Not much though. So this is going to be a course in complex geometry, so we're going to be talking about complex manifolds most of the time. Jacob basically already mentioned what complex manifolds are. So you have a smooth manifold, but you're assuming that sort of the transition functions of your smooth atlas aren't just smooth functions, but actually holomorphic functions on a domain in Cn. So when n is equal to 1, you're looking at holomorphic functions on domains in C, and then your complex manifolds are going to be Riemann surfaces, but you can do the same thing in every dimension. And we're also going to be looking at a particular class of Riemannian metrics that you can define on complex manifolds. So it's going to be the so-called Kähler metrics. So the particular Riemannian metrics. They probably won't actually be defining what a Kähler metric is until at some point next week. Won't need that in the beginning. So why are Kähler manifolds interesting? So they're a great source of interesting PDE problems. Maybe the most prominent one being is the Einstein problem. So you're looking at what Aaron was talking about, the one where you're looking for Riemannian metrics satisfying the Einstein equations that the Ricci curvature is equal to a constant multiple of the metric. Now I can pose that problem for arbitrary Riemannian manifolds. So there's nothing particularly complex or Kähler about it. So I can ask for arbitrary Riemannian manifolds satisfying the Einstein equations. What makes the class of Kähler manifolds especially interesting is that in that class, you actually have some hope of solving that problem completely. So if using the holomorphic structure that you have, this complex structure, to effectively reduce the problem to algebra in the end, actually solve the problem. And you can say, big deal. Every problem becomes solvable if I sort of restrict the class of admissible candidates. It's the empty class of manifolds or something like that, but the opposite is the case, and that's what I'm going to be trying to convince you of in the first week, more or less. That, complex manifolds, Kähler manifolds give you an extremely rich source of non-trivial examples. And in Riemannian geometry, if you want to do any non-trivial computations at all, sort of going beyond manifolds with a lot of symmetry or product manifolds, things like that, if you want to do any non-trivial computations and examples at all, then sort of Kähler manifolds are the first place to go. You can actually hope to do some interesting computations and solve the problems that you're posing yourself. But that, Jacob likes to say, that doesn't actually mean anything until you start going through some actual material. So in week 1, I'm going to try to give an introduction to complex geometry. And week 2, I call topics in Kähler-Einstein manifolds. And so the plan is more or less, I picked out a fairly recent result of Donaldson, which I think is pretty interesting, about existence of Kähler-Einstein metrics, not the big famous one that everybody's talking about, but something from a couple of years back. And that's what I want to try and explain at the end of the second week. And then I was just sort of trying to look for the most straightforward path to go from 0 to that result. And that's going to be the course, hopefully. So meaning in particular that I had to leave out a lot of standard material that all the textbooks spend lots of pages discussing. I'm not going to be talking about Hodge theory and Kähler manifolds, anything like that. That's not actually needed. But on the other hand, I'm going to be showing you some fairly advanced examples early on that are sort of relevant to the Kähler-Einstein problems that you wouldn't necessarily find in the basic textbooks. Okay, so start from 0. Lecture 1, holomorphic functions. So here's something that probably all of you have seen. Definition of holomorphic functions on C, so in one complex variable. So there's a definition and then various equivalent characterizations. I'm just going to write that down. Have an open set in C and a smooth function on that open set. So I guess usually in complex analysis, you don't a priori assume that your function is smooth. But so if you define what it means for a more general kind of function to be holomorphic, and then you deduce as a consequence that the thing actually has to be C-infinity smooth. But that's sort of interesting if you care about foundations. But in practice, all functions are smooth anyway, so might as well assume that. So then we say that f is holomorphic. By definition, if and only if, so that's the standard definition. For all points in my domain, the following limit exists. So that's a definition that never really made any sense to me until I sort of started studying several complex variables, and I'm going to talk about that later. Right, and then you show that this is actually equivalent to the Cauchy-Riemann equations. So Cauchy-Riemann says that ux is equal to vy and v sub x is equal to minus u sub y, where u and v are the real and imaginary parts of my holomorphic function. So f is u plus iv, and the complex coordinate z is x plus iy, and u and v and the x and y are real. It's Cauchy-Riemann. And then in particular, you get from this that holomorphic functions are necessarily harmonic, right? If you take one more x derivative and go through this and take the sum, you see that the Laplacian of u and v is necessarily 0. And then sort of the Cauchy integral formula to show that holomorphic functions are actually precisely those functions that admit complex power series expansions. So for all points z0 in the domain, there exists a radius r, so that on the level disk of radius r centered at z0, I have a power series expansion f of c. Some ak c minus c0 to the k for some for a sequence of complex coefficients ak that can be characterized in various ways. Okay, and you just do exactly the same thing more or less with functions of several complex variables. And the proofs of these equivalencies are almost the same as in the one variable case. So you can kind of reduce to the one variable case by inducting on the dimension, basically. That's pretty easy. I'm not going to do that. I'm just going to state the result. So proposition if you want. You have open set in Cn, so n complex variables. Smooth function on that set. And then the following are equivalent. So first off, that's somehow the correct generalization of the existence of the complex derivative. That's just saying that for all z naught in U, so if I take the differential df at z naught, so that's going to be a linear map from Cn to C. But in general, it's only going to be, if f is an arbitrary smooth function, this is only going to be an R linear map, even though I have two complex vector spaces here. Now, the holomorphic condition is precisely that this is actually a complex linear map. So if I multiply a vector by I here, like the result here is also going to get multiplied by I and not by minus I, or if you think about it long enough, then you see that this is actually exactly what the first definition means in one complex variable. And then you have the Cauchy-Riemann equations. If I just spell out this complex linearity, so it's just going to be the statement that U sub xj is equal to V sub yj, and U sub yj is equal to, which way? So V sub xj is equal to minus U sub yj for j, and n complex coordinates. And f is still U plus iv. And so, not surprisingly, this is just a statement that the function is actually holomorphic as a function of one complex variable if I fix any n minus one of the others. So for all j, f is holomorphic as a function of zj with all the other variables fixed. What else? And then you have a Taylor series expansion. Same statement for all points in the domain. There exists a radius, so that on a little ball around that point, I can write f of z as multivariable Taylor series a sub alpha C naught to the alpha, so in multi-index notation. So again, the fact that all of these conditions are equivalent in n complex variables, the easiest way to prove that is by reduction to one complex variable. So if you induct on the dimension, more or less. I'm not going to do that mainly because I'm going to be using the same argument over and over again in this lecture. So you're going to see it anyway. So in a more interesting context. Of course, then you say that. This is by definition what it means for f to be holomorphic. So I'll make a remark here. None of these conditions are particularly well suited for doing computations. What you would usually do is that you introduce what's called the Wirtinger differential operators. All right, one is best understood using Wirtinger calculus. So, what does that mean? It means we have, for example, on C, even in one complex variable, we have a function on a domain in C. So that depends on two real variables, x and y. Just some smooth function. But instead, we make a change of variables that instead of depending on x and y, we think of the function as depending on z and z bar. And then the holomorphic functions are the ones that only depend on z in a way. I mean, that's not rigorous in any reasonable sense, but this is how you do computations, right? And so just write that down. So you define these Wirting operators, d by dzj. So this is 1/2 dxj minus I d dyj. And d by dzj bar. So this is 1/2 dxj plus I times d by dyj. And then what you use them for is to decompose the differential of an arbitrary smooth function into sort of holomorphic and anti-holomorphic parts. So you define del f, this is the sum. So it's a one form that's going to be df by dzj, dzj del bar f. And then it's going to be true that sort of df has been decomposed like this. It's something you need to check. And the function being holomorphic is then precisely equivalent to the condition that this part here, the d bar part, vanishes. So then f is holomorphic if and only if d bar f is equal to 0. So for example, I'll just write down one equation that happens to be right. It doesn't actually mean anything. It's just, to show you how the symbols are used. So if you take something like d bar of mod z squared, so mod z is the Euclidean radius function in Cn, so it's just the sum of the absolute values squared of the complex coordinates. If you wanted to compute something like this, I would write this as d bar sum mod zj squared. So this is d bar of the sum of zj bar. Express any function that I care about as a combination of z's and z bars. And then the coordinate functions z are holomorphic, so the d bar just pulls right through and only hits the anti-holomorphic guys. And then it's just equal to the ordinary differential of these guys. So this is actually just equal to the sum of cj dzj bar, right? Because if I take the derivative of cj bar that has a priori that has a del bar part and the del bar part, but zj is holomorphic, so cj bar is anti-holomorphic, so the del part of cj vanishes. So del bar of cj bar is actually equal to d of cj bar. I mean, that's how you do computations with these guys. And then, okay, so there's something related to this that I have to mention, unfortunately. It's kind of, it's a piece of linear algebra, really. We don't really need it right now, but later on it's sort of inevitable to talk about this. So I guess if you do multivariable calculus, you usually you talk about the differential of a function, and then you extend that to differential forms. You take the operator d and extend it from scalar valued functions to differential forms, and you can do the same thing with del and del bar. If you take here f is a priori a complex valued function. talk about complex valued differential forms, you have operators del and del bar acting on forms also. And it's just a nasty piece of linear algebra that's useful at some point. Not right now. Write it down anyway, so more generally. Okay. You have your domain in C. You take differential K forms on that domain. And you tensor them with C, so meaning you're looking at complex valued K forms. K forms with complex coefficients. On U. And here K is between 0 and 2n. Right, so U is a domain in Cn, and I just view that as a smooth manifold in the obvious way as an open subset of R2n. So the number of real variables is really 2n. So this means we have differential forms in all degrees K between 0 and 2n. But we're allowing them to have complex coefficients, so just formally. And then no, this actually splits up as a direct sum for all integers p and q, so that p plus q is equal to k, of something that's called the space of pq forms on U. So what's PQ form? There's sort of elegant ways of defining this and less elegant ones, and I'm showing you the worst one, but that's again the one that you use in computations. So PQ form is a differential form of the following kind. So you have some coefficient function that depends on indices. What are my indices? J1 through Jp and K1 through KQ. So these are complex valued functions on my domain. And then I multiply that by sort of the basis forms, the indecomposable forms. And these are going to be dz J1 wedge dz Jp wedge dz bar Q1, K1 through dz bar KQ. Okay. So in other words, a PQ form is something whose indecomposable parts take the form that I need K differentials in total because I'm looking at K forms, but I'm specifying that I can write my form as a product of P factors that are only DZs, they're sort of only holomorphic, and Q factors that are only DZ bars, so sort of purely anti-holomorphic. So it's almost obvious that I can always do that. So if you want, what's going on is that so if you count degrees of freedom, if you count dimensions on both sides, then on the left-hand side you have K forms. So the space of K forms has dimension n choose K, complex dimension in this case because you're looking at complex coefficients, and then you're writing this as the sum P plus Q equals K. So how many possibilities do you have here? So you have n complex, here it's actually, so here it's 2n, because I have 2n real variables. It's the same 2n as here. And then you have n complex variables to choose from. There are z's and there are z bars. I only want p z's here and q z bars there. So I'm choosing p out of n and then q out of n. So I guess that's a true statement. Okay. And then you start talking about the exterior derivative acting on differential forms, and you want to decompose that as sum of del and del bar in the same way. I'm just going to write down the definition. So you have PQ forms. You have two operators, del and del bar. So del goes to P plus 1 comma Q forms, and del bar goes to P comma Q plus 1 forms. And, well, I guess, so if you take a form like this, it's written in this way explicitly, then if you want to take del of that form, what you do is you take an additional sum over all complex coordinates. So you have the sum that you have there anyway, and you differentiate the component functions of your form by DZL, and wedge the whole thing with sort of the complex differential DZL, all the other stuff that you have anyway. And same for del bar, so you differentiate only by DZL bar, you wedge with DZL bar, and then keep all the other stuff. And then it's going to be true that the exterior differential actually decomposes as del plus del bar. So in particular, the square of the exterior derivative is 0, d squared is 0. So if you expand the square of the sum, what this tells you is that del squared is equal to del bar squared is equal to del del bar plus del bar del is equal to 0. So what this means is that you can use each of the operators del and del bar sort of separately to define some sort of de Rham cohomology because their square is equal to 0. And they anti-commute. That's useful for computations too. Okay. Here? Well, it's the same actually, because del bar of CL is equal to 0. But I sort of prefer to write it in this way because a priori it's not even clear what d by dzj is supposed to be. I've defined it as a differential operator, but a priori it's not a vector field in any obvious sense. It's like a complex vector field. So that's kind of just a formal definition. Whereas DZL, this expression has a meaning anyway. Sort of, we wouldn't even have had to talk about del and del bar in the first place. I'm just taking a complex valued function and taking its differential that's just defined from multivariable calculus. But it's actually equal to del CL if you make the definitions in this way. Okay, so that's linear algebra. I just wanted to put that on the board to be done with it once and for all. I'm not going to be using it in a while. Well, actually, you're going to be using it in the exercises, so I printed some exercises that I'll give you at the end. Okay, but what I sort of really wanted to do in the rest of this lecture is to show you some basic properties of holomorphic functions and several complex variables, or really just one basic property in several guises. That's so with some work that's going to tell you everything you could possibly want to know about holomorphic functions. So I'm calling this strong non-degeneracy. That's not actually a thing. I just made that up, but it's. I'm going to say that. That's just propaganda again. the locus in Cn where k holomorphic conditions are satisfied. Is a submanifold, possibly with singularities. Of complex codimension K. So what's that saying? Just expressing the fact that you're sort of used to from standard one-variable complex analysis, and that's completely false if you think about real analysis and C infinity functions. So, for example, if you take a C infinity function and you ask for, what are the level sets like? In general, there's, preciously little you can say. I mean, the implicit function theorem tells you that if the differential is surjective, then the level set is going to be a hypersurface, so like a smooth submanifold of codimension 1. But in general, if that condition is not satisfied, if the differential is not surjective, like the level set could be pretty much anything, could even be an open set, because your C infinity function could easily be identically zero in some set and non-zero somewhere else. And that doesn't happen for holomorphic functions. So, the level set of one complex holomorphic function is always a complex hypersurface, always has complex codimension 1. It might not be a manifold anywhere, it might be critical points, and might be singularities in your level set, but it's really something of codimension 1 always, and it's not just an open set or something. So that's what I mean by that. So in one complex variable that's well known, I'm going to write down a formal statement in n complex variables, and the proof is going to be by this principle of sort of inducting on dimension and reducing to the one variable case, sort of by slicing. So this goes by the name of the Weierstrass preparation theorem. There are lots of Germans in this business. So it's saying the following. Suppose you have a holomorphic function on a neighborhood of the origin in Cn, for simplicity. You use an open set in Cn containing the origin, so that's our base point. And you assume that it actually vanishes at the origin itself. And then you make one assumption, which is that f of z1, 0, is not identically 0. To set all the variables equal to 0 except for 1. And you're assuming that's a holomorphic function of z1. And you're assuming that that's not identically 0. So basically you're assuming that this guy here, as a one-variable holomorphic function, has an isolated singularity at the origin. And that's, if f itself is not identically 0, you can always achieve that by rotating your coordinate system. There has to be some coordinate system in which this is satisfied. So that's a reasonable assumption. So then the statement is the following. So unfortunately, it's not going to fit here. So there exists a smaller neighborhood, U prime, containing the origin. And holomorphic functions g and h on that smaller neighborhood such that the following holds. f is equal to the product of these two guys. That's not very exciting. Second one is that h doesn't vanish at the origin. It's not very exciting either. It's just saying that h doesn't actually vanish in some small neighborhood of the origin, meaning that you can actually divide by h. So 1 over h is a nice, well-defined holomorphic function as well. Real content is about the shape of G. So you can actually assume that G of Z is equal to Z1 to the D plus A1 of W Z1 to the D minus 1 plus and so on AD of W, where I've written Z as Z1 comma W. So W is all the other complex variables, the remaining n minus 1. And these functions AI are holomorphic and vanish at the origin. And this thing here is what you call a Weierstrass polynomial. So in complex dimension 1, this is an extremely well-known statement, just saying that holomorphic functions vanish to finite order. That's exactly this kind of non-degeneracy that I was talking about, right? So it's saying that if you have a holomorphic function on a disk in C that vanishes at the center of the disk, then you can actually write it as z to the d, where d is the multiplicity of that 0 times an invertible holomorphic function. And that's a kind of non-degeneracy that's completely absent for arbitrary C infinity functions. That's sort of the right version of stating that for functions of n variables. It's kind of a confusing statement, but the picture is extremely clear, and the proof is essentially by picture. So, so the technique that you use in the proof is something people like to call slicing. And the principle that you use here to push the slicing through is called positivity of intersection. Positivity. Intersection. So what's the picture? You have Cn minus 1, that's with coordinate w, that's of the n minus 1 remaining variables, and you have C with coordinate C1. And now you're asking what does the level set of my holomorphic function look like? Well, to find out, I'm going to slice it with, take the level set, so f inverse of 0. And these guys here, the vertical axes are complex one-dimensional, so I'm going to slice it with these complex one-dimensional guys because I completely understand the picture in complex dimension 1. And I have a function that's sort of not identically 0 here, so it's certainly not identically 0 in, like if I take a box neighborhood, my function's, it's not identically 0 on this axis, so certainly if I make my neighborhood here small enough, it's not going to be identically 0 on the, it's actually going to be non-zero on the boundary of that neighborhood. And then I have these disks here, basically, so the vertical directions are going to be disks in C, and I have a holomorphic function on a disk in C that doesn't vanish on the boundary of that disk, so I know that it only has finitely many zeros in the interior. And actually everything varies kind of smoothly here, so you know that the number of zeros in that disk is actually constant. So what I'm saying is that you're slicing with these vertical guys, and these are just disks in C. And in each of them, so if the restriction of your function to that slice is going to have the same constant finite number of zeros. So that's the picture that you get. maybe in one of the slices you're actually going to see a double zero, so that's sort of two simple zeros coalescing into a double zero as you move the slice, as you move the parameter. And so if the number of zeros in each slice is just d, that's the degree of this Weierstrass polynomial. So somehow you have a multiplicity. If you look at the central slice, this coordinate axis, you have a zero of multiplicity d. And as you move the slice, this sort of resolves in generically d separate single zeros of multiplicity 1, or possibly exceptionally some zeros of higher multiplicity, like here double zero. And this is so positivity of intersection means that you look at the intersection number of the vertical slice and the zero set of the holomorphic function. And that's always going to be a positive number, basically because you have an underlying complex structure. That's this thing that one-dimensional holomorphic maps give you orientation-preserving conformal maps. That's emphasis on orientation preserving. So the intersection number of the slice and f inverse of 0 at each of these points is a positive number. Meaning you can't have the thing that's sort of typical for smooth real valued functions, that you have 2 points in the level set and they sort of come together and cancel out. So the intersection number has to add up. So it's sort of a priori finite. It's kind of conserved. We'll write that up as a proof. So let P1 of W, PD of W be the zeros of my function restricted to the slice with parameter W. I mean, a priori D could be infinity because that function might be identically 0, but we've been assuming it's not identically 0 in that central slice, and that allows you to say it's not going to be identically 0 for the nearby slices at least. A priori D could actually depend on W, but that's not the case by this argument I just told you. It's positivity of intersection, so if the number of zeros is conserved. If you don't like that, because it's actually extremely non-rigorous, the rigorous proof is going to come out of the argument anyway. So now what you do is you want to define your Weierstrass polynomial g of z. What's that going to be? That's just, it's a polynomial on each slice. That's what it is. So g of z is just the product j equal 1 to d z1 minus pj of W. So you're counting with multiplicities. If one of the zeros has multiplicity 2, then you're actually counting it twice in this list. So that's going to be a Weierstrass polynomial. And the only thing you have to show is that this is actually a holomorphic function of all the arguments. So if it's trivially a holomorphic function in Z1, because in Z1 it's just a polynomial, but then the question is, why do these zeros vary holomorphically as I'm varying the slice? That's sort of the question. Need to show. Well, that's maybe not a very well-defined statement, because I'm implicitly taking some sort of ordering of the zeros, and then I have branches that are crossing over. It's kind of nasty to follow through. What we're really asking is, why are the coefficients of this polynomials holomorphic functions of W? So in other words, why are the elementary symmetric functions in the PJs holomorphic functions in W? So those are defined independent of any ordering. So we need to show the elementary symmetric functions of P1 of W, P D of W are holomorphic functions of W. you know, the sum of all of these guys, or the product of all of these guys, are all the other elementary symmetric polynomials. So to prove that, we basically go back to Newton. So Newton tells us that every elementary symmetric polynomial in a bunch of variables can be expressed as a polynomial in the power sums of these variables. PL, P, J from 1 to D to the L, that this guy is holomorphic in W. And that has to be true for all integers L. Right, so that's the sort of identity where you say that P1 that sort of identity, that, you know, you care about some elementary symmetric function, some elementary symmetric polynomial of a bunch of variables, and, you know, this is a sum of the first powers, and this is a sum of second powers, and you can reduce that to a sum of powers in this way. And Newton tells us that that actually works for arbitrary elementary symmetric functions. I can always reduce them to power sums in this way. So it suffices to consider expressions of this form, and these are actually much nicer. So this is something that we can control using analysis. No, notice that. The sum of P, J of W to the L, this can be written as a contour integral of, you know, absolute value of C1 equal to some, any radius really. So you're doing like, you know, you're fixing W, you're restricting to one of these slices. So that's a disk, and you're doing a contour integral around the boundary of that disk. It's just a one-dimensional contour integral. And, you know, if you want, that's a residue theorem, something like that. It tells you that this is actually equal to contour integral of C1 to the L. Yeah, F prime of C1 W divided by F of C1 W dZ1. So in particular, if you take L equal to 0 formally, if L is equal to 0, then the sum just counts the number of zeros of that holomorphic function in the slice associated with W. So you express it as a boundary integral, and, you know, F is holomorphic by assumption, so it's smooth. So the integrand depends smoothly on W. So you have an integer, which is the number of zeros, depending continuously on a parameter, which is W, meaning that the integer has to be constant, so the number of zeros is the same. And the same argument, because F is holomorphic in W, we have this expression which is holomorphic in W. You're integrating with respect to a parameter, so the whole thing actually varies holomorphically with W. So independent of W and finite. Yeah. Sorry, say that again. Yeah. Okay, so this is holomorphic in W. So I'll just write that down as another slogan. So this theorem, the Weierstrass preparation theorem, tells you everything basically that you want to know about the structure of level sets of holomorphic functions, or more generally of analytic sets. What's the use of the theorem? It's called analytic sets. So meaning sets of the form, the locus where k holomorphic conditions are satisfied. So f1 equals fk equal to 0 for all fj holomorphic. So that's imposing conditions is a natural thing to do, and holomorphic functions come up everywhere. So that's a very natural class of sets to consider. And Weierstrass tells us a lot about these sets. And on the problem sheet, I'm going to give you some exercises, sort of paradoxical analytic sets with properties that maybe you wouldn't expect from this slicing picture. So that's an interesting topic in its own right, to understand the structure of analytic sets. You can say a lot, but there are all sorts of interesting pathologies. Okay. Then one more thing, that's sort of another basic theorem in several complex variables that follows from the same technique, and that just want to push through today. So it's really the same technique, and that's why I want to show it to you, is the Hartogs theorem. You can almost guess why it's true, based on this Weierstrass preparation thing, but it's just sometimes called the first real theorem in several complex variables. I mean, certainly the first one was discovered. So that's something that doesn't have an analog in complex dimension 1. That's sort of the first genuinely new phenomenon, if you want. So application of the same logic. And I'm going to state it very informally and only for two complex variables, because then I can draw an unambiguous picture. And also then there are several ways of generalizing the result I'm going to write down to more than two complex variables, not just only one way. So in C2, the following holds. Just going to draw a picture. If f, it's going to be an implication. If f is holomorphic on a region of the following form, so these are my coordinates z and w in C2. Your first exercise is to think about what this picture actually means, but it's, I'm basically taking a neighborhood of the origin and I'm removing a smaller neighborhood. But I'm doing this sort of in a product way, piecing together products of domains, disks and annuli in complex dimension 1. This means that f extends holomorphically. Holomorphically, so to the whole neighborhood of the origin. So that's clearly not true in complex dimension 1. If you have a holomorphic function on an annulus, it might have a singularity at the origin. Two complex variables, you have that. And so the right way to think about this, why is this theorem true, is the following. If you think about the simplest functions, the simplest holomorphic functions in complex dimension 1 that actually have singularities, that's meromorphic functions, so quotients of holomorphic functions where the denominator has zeros. So the moral reason here. It's not a proof at all in any sense. F is actually equal to G over H, where G and H are holomorphic. And then the singular, so if the set of singularities of F is equal to the zeros of the denominator, but by what we just learned about zeros of holomorphic functions, you have this Hartogs thingy, this annulus, in two complex variables. But the zero locus of G is going to be something of complex codimension 1. It's like a holomorphic curve, or a Riemann surface, if you will, and that's going to stick out of the inner box. So if you assume that the thing is regular on this annulus, then it actually has to be regular everywhere, because the orange curve doesn't actually exist. And the proof is one line, more or less. It's almost exactly the same thing that I already showed you. So you slice. Slice by these vertical lines. The intersections of these vertical lines with my domain are going to be, this here is going to be a disk in C, and this here is going to be an annulus. So big disk from which I've removed a smaller disk. This is a disk in C. It's an annulus in C. It's a W-axis. I restrict my holomorphic function to this slice. Get the holomorphic function on annulus in C, and I know that holomorphic functions on annuli in C have Laurent series expansions. So that f of CW is actually going to be equal to, I need to allow for negative powers. AK of W times Z to the K. Now I'm asking what could these coefficients AK be. So again, I'm using sort of the residue theorem or Cauchy's integral formula to compute these coefficients in terms of the function as a contour integral. So that AK of W is actually equal to 1 over 2 pi I guess, integral C equal to 1, if you want, f of CW divided by Z to the K plus 1 dZ. This very convenient expression for how these Laurent coefficients depend on the parameter W. And so this implies the following. AK of W is holomorphic in W because I'm integrating something holomorphic with respect to another parameter. Is holomorphic in W. AK is actually equal to 0 in the region L. L is of the part here on the left where my slice is a disk in C, because then I have a holomorphic function on a disk, and then the Laurent series expansion can't have any coefficients of negative degree. So here my slice function is actually holomorphic. So all of these Laurent coefficients vanish if k is negative. But this means that the AKs for k negative are holomorphic function of one complex variable W that vanish identically in a non-empty open subset, so they actually have to vanish. They're defined everywhere, so they have to vanish everywhere, meaning that the function has to be extend holomorphically to the whole thing because it can't have any negative Laurent coefficients sort of in the intermediate region. Less than 0 for all W. Okay, that's it. Tomorrow I'm going to tell you what complex manifolds are. Don't forget to pick up your homework. Thanks.